All right, so section 13.2, limits and continuity. What we're going to do is we're going to go back and do the same kinds of things we did with limits when we talked about functions of one variable, and now we're going to do it when we're doing functions of more than one variable. So what I want you to do first is to just sort of think back and recall when we, and I know it wasn't me, I know it was somebody else that worked with you, but when we talked about the limit as x approaches a of the function f of x, we had to consider the limit as x approaches a from the left of f of x and the limit as x approaches a from the right of f of x. You guys remember that? Okay, in order for the limit to exist, it has to be the same from both sides. Well, this becomes a lot more complicated now. Much more complicated. Much more complicated for the limit as xy approaches a particular point a, b on our function f of xy, as just a specific example. And the reason is because xy may approach the point AB along infinitely many paths. Now, for nice functions, nothing much changes, and that is a non-math term right there, nice functions. So let me show you what I mean by that. So let's say, for example, this is what I'm going to deem it right now as a nice function. We're going to take the limit as x, y approaches, and I'm just going to choose 1, 2 as the ordered pair. And we're going to just use the function x plus y minus 4. So back in Calc 1, when you first encountered this topic, these were the kinds of functions you were dealing with then as well. They didn't have y in them, but they were very clean and simple. And you had the ability to do what? Just to plug the number in, right? So if I do that, I can see on this one, of course, I would have the same ability. I would have 1 plus 2 minus 4, which gives me a total of what is it? -1. Yeah, -1. So that looks and feels just like the stuff we did before. Like, what's the big deal? Okay. Well, this problem of not nice function. Okay, so the problem comes on not so nice, again, a very non-mathematical term, functions. And then I'm going to give you an example of one that I'm deeming as not so nice. And I'm going to let you tell me why I think it's not so nice. So let's say we want to do the limit of xy as it goes to the number 1, 2. But my function is now xy minus 2 over x minus y plus 1. So why is this one not so nice? It's worse even than that. What would happen if you tried to do what we actually just did on the last one? Yeah, it's an indeterminate form, right? Because what do you get on top and on bottom? Yeah, we get, I mean, if we tried to do this, we would get 0 over 0, which is an indeterminate form. And that's a problem. And even worse is that there's no factoring or simplification I can do to sort of get rid of the problem on this particular one, right? That's really unfriendly. And so then we have to decide, well, does the limit exist or does it not exist? Is there a hole in it? Because if there's a hole, that's not a problem, right? But if there's something else going on, like sort of like a three-dimensional asymptote kind of a feature, that would be something that would be a problem. So what do? So we will treat this differently. And I'm going to go through several different kinds of things that show how this gets treated differently. Okay, so this isn't as simple. We treat it differently, and bam, here's the way we do it. I'm going to go show you several different things. The first thing I want to show you is something that you have seen a version of before. So does everybody have everything on the screen written down? Are we good to continue? Okay. So this is something that you absolutely loved when you saw it before. I know you did. It's definition 2.1, and it's actually the formal definition of limit. All right, so we're going to sort of three-dimensionalize, if you will, the definition of limit you saw before in Calc 1. So let f be defined, and the defined part is going to be a little different. This is going to be defined on the interior of a circle centered at A, B. Now, I know this is really drawing back on what you did before, but any idea what this might be sort of analogous to when we did things in 2 dimensions? Like, why am I creating a circle right now? What did I have before when I was dealing with 2 dimensions instead of 3? Nope, wasn't a line. It's a good guess, though. It's a 2-dimensional object. We were working with curves and or lines, but what did we do to create this sort of location around the point A? Like in 2 dimensions, this right here just had point A. And we were looking at an image that was something like, I'll draw the curve that you suggested, James. And we wanted to talk about what the limit was right here. And so what we did is we looked at sort of this space around here, and we created an open interval. Remember open intervals? The idea being that if you're in a small interval around it in one part of the graph, that you'll have to be in a small interval around it in the other part of the graph. That's the image that we had in mind back in the day. So we had this sort of an open interval here. So what's that?
Plus or minus delta.
Yeah, and so we had delta and epsilon. I'm going to get delta and epsilon in here in a minute, yeah. Well, the problem with 2 dimensions is that when we do this in 2 dimensions, think about those contour curves you were graphing in the last section, and you had something that looked like, I'm just pretending, this is a mountain range, pretend. So, I don't know, your contour curves looked funny, something like that. Well, if I want to know what the limit is at this particular point right here in the middle of all these circles, what I have to do is I have to have an open interval around that point. But an open interval in 3 dimension, or in this 2-dimensional plane right now, an open interval in the 2 dimensions would actually be a circle. So we create sort of a circle like this, much like we created this interval down here like this. Okay? And then we can talk about what happens at the height or altitude if you want to think 3 dimensions of this particular shape. All right? So we don't, in fact, have a cliff. We actually have a peak or a valley, or we just have a point on the mountain itself. Okay, I need to cut these off just so that I have some space. Hang on. All right, and it doesn't necessarily, so we're going to say except possibly at the point AB itself. And we had that same kind of a statement in the previous definition when we saw it before, is that you might have a hole in the graph and that wouldn't affect limits. So it's okay if it weren't actually defined at the point itself. We could still get infinitely close to it. All right, so we say that the limit of our function f of xy as xy approaches AB is the limit value L if, and then Caleb, here's your epsilon and deltas you saw before, if, and I'll write it out in English instead of symbols first. So if for every epsilon greater than 0, there exists delta greater than 0 such that when f of xy, our function minus its limit, is less than epsilon, that this happens, I should say, sorry, this happens whenever 0 is less than the square root of x minus a squared plus y minus b squared, and when that radical is less than delta. Now that looks a little different. In 2 dimensions, we just had an absolute value sign. Why are we getting this description right here? Where's that coming from? There's at least 3 legitimate answers I can think of as to where you could say that's coming from. Distance formula. It looks a lot like the distance formula. Anyone else recognize it as something different? Different but related. Formula for a circle, which is intimately related with the distance formula. And someone also might recognize it as it's related to the Pythagorean theorem. Those 3 concepts are all really the same concept. We teach them in a different sort of a viewpoint, but that's what you're doing. And it's coming from, I like the idea of it being related to a circle because we talked about up here being the interior of a circle. So I kind of like that particular viewpoint at this point because of what we're talking about. We're talking about the interior of the circle being close, right, being within delta. So in other words, if you were looking at this circle that we're talking about, that this distance right here would be delta in this circle. So that's kind of nice.
What's the D there?
What's the which part? What?
You have less than square root of all that, less than delta. What's on the left?
It's x minus a. Oh, this is a 0. It's a 0. It doesn't look like a very good 0. You're right. I'll make that look much more 0-like. Thank you. Yeah. And that 0 is a part of the original, definition when we describe this as 2, but it's almost kind of silly. We just are just talking about we don't have a collapsible sort of area here. I mean, we can't be talking about a single point itself because obviously it's greater than or equal to 0 automatically because we're talking about a square root, right? So we're just eliminating the possibility that it's actually a single point and not really a circle. That's all we're doing. Okay. We're going to use this, but not in the same way you used it before. So I promise we're going to come back to this particular definition. I'm going to show you how it gets used, but we're going to look like we're going to deviate from this just a little bit first into something you'll like perhaps a little bit better for the moment. So we're going to do an example. We're going to compute the limit of a nice function, okay? So we've got the limit of xy, the limit as xy approaches 1, 3 of the function x squared y over 4x squared minus y. So if it is in fact a nice function, I told you it was, we should be able to do just what? Just plug the numbers in. And even if it's not looking like it might be a nice one, because this one doesn't look especially friendly, not as friendly as the first example I gave, we should still try to see if that would work. So what happens when we try that on this? What do we get on the numerator? 3? Mm-hmm. And in the denominator? So we get a limit of 3, right? So you're going to do a couple like that when you're doing your homework. When I give you this homework assignment, it's going to look long. Keep in mind, I just told you you're going to have some of them that will be like this. They took you a whole 5 seconds to do, right? Okay, so please bear with me on that. Now, it's really easy to show that a limit exists if it's a nice function. It's also easy to show a limit doesn't exist. Let me show you what I mean by that. So for a limit to not exist, what did we have to do in Calc 1? If a limit doesn't exist, what was one of the ways in which it didn't exist? Okay, a hole in the graph, it exists, right? So visually, what would happen? Might go to infinity. What else might happen? Yeah, or infinity from one way or another, right? So the problem when the limits don't exist is that the two sides don't get close to the same value. It was all about the two-sided limit, right? We don't have the two sides approaching the same thing. So for a limit to not exist, we must show that along two different paths, we get different limit values. Now, let me go a little bit further into this, because I made this comment before, but I didn't really describe it very much. I told you something about that there's infinitely many paths. So imagine having a point in 3 space and looking at its contour graph. So this is my point. It's actually on a 2-dimensional plane if I'm looking at a contour graph. And if I'm taking this point where I'm starting out, let's say this point is my point x, y, and I'm trying to arrive at this point AB, which is in essence what I'm doing when I'm working on these limits. I could just take a straight line to get there, right? Like shortest distance between 2 points is a straight line. That's one path. That's not the only path that will get me there, right? If we were dealing with something realistic, real life kind of stuff working on this, we might have to take roads to get there. We can't drive straight across the field. So there might be something where I would need to do like this to get there. I might be able to go straight there. I might, for some reason, need to do something like that to get there. There's infinitely many ways I can get from one point to the other. So, in order to show that a limit doesn't exist, I just have to take 2 separate paths that don't end up with the same limit value. And I know that sounds a little bit tricky, but that's actually the easier of the 2 options. Showing the limit doesn't exist is the easy part. So let me show you an example of how that works. Now, here's the nice thing. Your textbook's not going to make you figure out, at least not yet, which ones do and don't exist. They actually tell you, show they don't exist. So that's a very friendly feature right now. These directions are exactly like your book says. It says show that the limit does not exist. So you know going into it that that's going to happen. Yeah.
So we're still dealing with the nice functions, right?
No, these are going to be functions that aren't going to be nice. Yes, we're not going to be able to just plug the values in and get a value. And so you'll see that real quickly here, Jordan. So let's take the limit as xy goes to 0, 0, and we have 2y squared over 2x squared minus y squared. And not nice, right? And very much like Nathan pointed out earlier, it's an indeterminate problem. That's what makes it not nice, is that it's an indeterminate form. And in indeterminate form, anything can happen with limits. 0 over 0 can equal lots of stuff, because it's not really 0 over 0, right? That's just evaluating the function, and we want to find the limit of the function. So this has either a whole or an asymptote, and we really don't have a way, I mean, basically from a two-dimensional sort of perspective, we don't really have a way of deciding which one it is yet. So we're going to take two different traces. So a trace, remember, is just a path. So I'm going to pick, there's some common traces, let me just say that. So some of the common traces that you might pick are x equals 0, y equals 0, or x equals y. They may not always be the ones you want, but those are some good ones to start with, okay? So we're going to test along the trace x equals 0, and I'm going to do along the trace y equals 0 in a moment. So let me show you how that works. So if we're testing along the trace x equals 0, what it means is that I am setting the x value to be 0, and I'm going to approach the value 0, 0 along the trace of x equals 0. So in terms of a picture, if that helps you to think about it, we're trying to approach the value that's at the origin, right? This is where we're trying to get to. We're going to approach that value along the path where the x value is already 0, which means where are we on our picture? On the y-axis. So we're limiting our viewpoint to approaching this from one of the directions along the y-axis. That's how we're approaching it. We're fixating on that particular approach. So in terms of our equation, what that means is that I have 2y squared over negative y squared, because x is in fact 0, right? So I can just put the 0 in for x. That is the function value itself. And then notice that this does in fact have the ability to simplify now, right? What does this become? This value is negative 2. So along the trace where x is equal to 0, the limit value is negative 2. So far so good? Okay, we're going to try along the other trace, along an other trace, and the second trace I'm going to try is along the trace where y equals to 0. Again, there's nothing special about those. I could try lots of different things. Those are just often convenient values to try because we're already approaching the value of 0, 0 here. So we're going to do this, along the trace y equals 0. So I've got the limit of x 0 approaching 0, 0. And then now if you take a look at this function, what does this function actually become? Yeah, it's 0 over 2x squared, which is 0. So this limit's 0 because the function's actually 0 on this one. So along this trace, the limit value is 0, and these two limit values don't match. This is a problem. So this actually proves, since these two are not equal, the limit does not exist. Just like in Calc 1, when the two sides did not approach the same value, the limit doesn't exist. Okay. What if we had gotten the same value for each of these? What would that tell us? Keep trying potentially other options. It doesn't actually tell us anything, right? Because in order for the limit to exist, it has to have the same limit value along every trace, and there are infinitely many traces, so this is a problem, which is exactly what I'm going to write down next. So showing a limit does exist. And again, just like Jordan had asked earlier, we're talking about these indeterminate forms, these unfriendly functions. I mean, the friendly ones we don't have problems with to deal with this with anyway. This is harder. Conceptually, we must argue that the limit of our function as xy approaches a, b exists along every path x, y as it approaches a, b. But as we said, there are infinitely many paths. So now what? Because infinitely many is not a number that I really want to work with. I don't want to do anything that's going to take me infinitely anything. So what next? Well, let me give you a definition that will kind of help establish what we're going to do next. And then we'll try an example. Okay. Let me know when we're done writing. I don't want to switch the slide just yet. Are we good? Nidra, Taylor, everybody all? Okay. All right, so I'm going to write down, not a definition, I didn't mean that, a theorem. Theorem 2.1. Suppose that f of xy minus L is less than or equal to g of xy for all points xy in the circle centered at AB. Except possibly at AB itself. Okay, so we might have to exclude that point just like before. Then, if the limit of g of x, y equals 0, all right, let's be clean. xy is approaching AB. I don't have that in my notes, but I should have it on your screen. All right. Then the limit of f of x, y is going to be 0. This is a very practical point to make. It really follows straight from the definition 2.1 that we already did before. All of the pieces at the beginning are establishing that we have basically the same setup as the definition had. We've got this function, it's got this f of x minus the L, and it's less than some other function g of x, so it looks a lot like it being less than, what was it, epsilon? Isn't that where we had our epsilon in our definition? We've got this circle centered at the point AB. That's the part where we had the distance formula basically being less than delta, right? That's what that's talking about. And we're saying that if we have the limit on the right-hand side is equal to 0, then we can sort of apply the squeeze theorem like we did in Calc 3, right? I mean, if we've got an absolute value here, we know that it has to be, this piece has to be greater than 0, right? So then if this one is approaching something that's equal to 0, then we're getting something sandwiched in between. The squeeze theorem did that for us back in Calc 3. So that's what's going on here. We're sort of squeezing out any other options here, so that the limit's going to be the same value for the limit. So let me show you an example of how this works. So we're going to show that the limit exists. And this is going to feel somewhat like using definition 2.1 and theorem 2.1 kind of combined. So that's what we're going to do. Here is the example we're going to work with. We're going to take the limit as xy approaches 0, 0 of the function 2x squared sine of y over 2x squared plus y squared. So in looking at this, the first thing you should sort of in your mind rationalize is that sine y is not doing a lot. Agreed? Because sine graphs and cosine graphs do what? They just oscillate between -1 and 1, right? Same thing when we did sequences and series, right? They don't really do a lot for us, but bounce around. They are trapped, which is helpful. But if the other pieces are going to 0, that piece is not going to sort of throw things off going to infinity or anything like that. So that's a helpful piece of information to keep in mind. We're going to start this problem much like we started the last one where we were showing things didn't exist. We're going to look at the 3 traces, and then we're going to go from there. So we're going to look first, in fact, I'll write that in just so you have it written in your notes too. So we start by looking along several traces, or paths if you prefer. So the first one we're going to do is we're going to do the path if x equals 0. Okay, so that's the trace we're going to do. So we want the limit as 0y goes to 0, 0. And what does our function actually look like if we use 0 in place of x? We get just 0. So this limit is 0 because we get a 0 in the numerator and we don't get it in the denominator, right? Okay, for the function itself. Let's do the path where y equals 0. So this is the limit as x0 goes to 0, 0. So what does this function look like? I'm going to write this a little up here differently just to make sure you're all thinking that this was what we had. This was actually 0 over, which one were we doing? X is 0, so it's over y squared, which is why it was 0. We get 0 for a different reason though this time, right, Caleb?
Sure.
Why are we getting 0 on the numerator on this one?
Sine.
Yeah, because sine of 0 is 0, right? It's not because of the x value this time. So I technically have 0 on top and I have 2x squared on bottom. That still gives me a limit of 0, right? Because the function itself is 0. What if, I told you that a third option that we will often try is along the trace y equal x, which is the straight line at 45 degrees basically, or pi over 4, if you're thinking in terms of radians. So this is the limit of, and we'll put xx going to 0, 0. We could equivalently put yy if we thought that was prettier to look at or something like that. I'm going to use x. So my function actually ends up looking like 2x squared sine of x over what? What would I have on bottom? 3x squared. And you might look at that and think, oh, finally something actually simplified and it doesn't look like 0, and at least at the get-go, right? So at least this one has a little bit more interesting results. So this actually would be 2/3 sine of x, but the limit of that's going to be what?
0.
Still 0, because I still have sine of 0. And unfortunately, this is one of those cases where we would have loved for it to be different. If it had been different, we'd be done. Agreed? Yes, we would, and we would say the limit doesn't exist. But they're the same, which means we still haven't proved anything. Right? That's what it really means. We haven't proved anything. So, if the limit does exist, the one thing we do know is that it would be 0, right? So it's either 0 or it doesn't exist at this point, because we've got 3 cases where we found limit values of 0. So if it does in fact exist, it's 0. So if the limit exists it must be 0. So we're going to consider taking our function value, which I will actually write in the function in a moment, minus the value of 0. And that's what we think it is if it exists, right? All right, so let's write that in. The minus 0 part's uninteresting, but this is the 2x squared sine y over 2x squared plus y squared in absolute values. All right, so I'm going to make a change that makes the problem something different and something easier to work with at the same time. Okay, so that's my goal. I'm going to change something. What I'm really doing, actually, I'm going to go back to the slide before, so if you're still writing, just pause for a minute. What I'm trying to do is I'm trying to create a g of xy function over here that I can work with and know a limit for. That's what I'm going to do. So I'm actually going to change to a different function, which is why I'm going to end up getting a less than or equal to sign instead of an equal sign, because right now I've still had an equal sign, right? These two steps before are actually equal to each other. So what I'm going to do is I'm going to write down the same thing without the y squared. So this is 2x squared sine y over just 2x squared. Now, I argue that that is bigger than the value I had before. Why would that be bigger? I reduced the bottom. If you divide by something that's smaller than you were previously dividing by, and it would be smaller because y squared is a positive number, right? So I've definitely made the denominator smaller than it was before, which means I've made the fraction bigger than it was before. But doing so was actually helpful to me because what do you notice you can do to this problem? You can reduce something, right? You actually have the ability, in fact the 2 goes away too, of reducing this to simply sine of y. Okay? So I'm going to have to switch slides because I've run out of space. Does everybody have things written down so far? Okay, your work is going to continue on with this sort of line of inequality. So you're going to end up with, you know what, I think I might have space for at least that line of it. I have sine y here. Okay. So, I mean, this is what we've actually created. This right here is my g of xy function from Theorem 2.1. Okay, so that's the g of xy that I'm going to be talking about. So think about then the limit of g of xy, because that's what that theorem was all about. And I want my xy to go to the same point, 0, 0, because that was the values that was going to in our f of xy function. So this is the limit of the absolute value of sine of y as xy goes to 0, 0. And that value is 0, which is what I needed it to be in order for that theorem to actually be helpful, right? If it weren't 0, this wouldn't work anyway. This would be a problem. Since the absolute value of my function, f of xy, minus 0, is less than or equal to g of xy that we just created, and the limit as xy approaches 0, 0 of g of xy equals 0, what does that tell us? Right, by Theorem 2.1, the limit as xy approaches 0, 0 of f of xy actually is 0. Now this doesn't work if the limit's not 0. I mean, so it would be unhelpful in that regard, right? Yeah, I mean, obviously this would be a problem. So if we had gotten that g of xy did not have a limit of 0, we would be sort of up a creek at that point, and we would have to go back and reevaluate what we did and see if we could find a way to fix that part of it. So, never in your life were you so happy to not have something exist, right? It's a lot more work if these particular ones exist. All right, there's one other thing in this section. What was the title of this section? Did you write it down? Yeah, limits and continuity. Obviously a related topic. So let's take a look at continuity here. All right, so suppose f of xy is defined on the interior of a circle centered at AB, period. Notice I'm not going to say except possibly at AB itself. That would be unhelpful for talking about continuity. Okay, so it's centered at AB. So we say that F is continuous at the point AB if the limit of f of xy as xy approaches AB equals f of AB. And if it is not continuous, what do we call it? What's the other word? Discontinuous. Right? You guys were just thinking too hard, I know, I can tell. Yeah. This is exactly like what we did when we talked about continuity before. It's continuous if the limit is the same as the function value. That's all it says. It's continuous if you're actually able to plug the value in. So on the last problem, while we found that the limit was 0, it wasn't a continuous function because the actual value was not even able to be plugged in, much less actually be the same, right? So continuity has to do with being able to have the same function value as the limit value. That's all this is saying. And we're going to do an example. Okay, does everybody have it written down? All written down? Okay, great. So we're going to determine all values where the function is continuous. And we're going to use this function. Minus x squared minus y squared underneath the square root. This problem is going to feel a little bit like stuff you did in the last section. So in order for it to be continuous, what has to be true? You have to be able to plug things into it, right? Which means at least a little bit of what we're looking at here has to do with finding out what the domain and range might be, right? And domain's the one we want for this one. Domain's the numbers I can plug in, range is the values I get out. Okay? So thinking in terms of this problem, what do you do to look at this and talk about domain?
You want to see if something would be negative under the radical.
Right. In particular, what's under the radical, and I'm going to just rephrase what you said in the opposite direction. What we want is we want what's under the radical to not be negative, that is to be positive or 0. So we can start by taking what's under the radical and finding a inequality that says that we want what's underneath the radical to be greater than or equal to 0. What would be a nice way of rewriting this particular inequality?
0, and then put x squared and y squared in the middle, and then
Okay, we don't have a triple inequality on this one, so we don't have like a left side and a right side inequality.
9 is greater than x squared plus 9.
What was that, Nathan?
9 is greater than x
All right, so I agree. I think it would be helpful to keep the x squared and the y squared together. And since they're both negative on the left, I would be tempted to move them to the right. On this particular one, I don't think it would be very friendly to solve for y. It would just look more complicated instead of being more easily determined. I'm going to rewrite this because you might find it easier to think about if I rewrite it this way. If that were not an inequality and instead it said an equal sign, what would this picture look like? A circle. So the picture still looks like a circle. It's just that it's a circle that's going to have some shading. Where's the shading going to be? Oh, let me pause for a second. Inside, yeah. Okay, so it's a circle. Where's the circle centered?
0, 0, 0.
All right, it's centered at 0, 0 with radius of 3. What's wrong?
You're not a perfect circle drawer, that's all.
Well, I'm doing my best.
Wow.
That's a pretty good circle. I just don't have, look at that. We'll go with that. How's that? That's a pretty good circle. And then the shading should be inside, you guys said, right? So I'm going to make my colors clash because I've got red inside of a pink circle now. You guys can't see all the colors quite the same as my screen does, but... All right, so this is the picture that we're getting. Now, in the back of your book on this one, I think this was an odd one that I was looking at the back, just curious as how they were going to word what the answer was going to be. They just leave it written like this, which I don't find to be a very intuitive description of what they're asking you to find. They actually say in the problem to determine the values where the function is continuous. So I'm going to have you write out what this actually means, because this has a very distinct picture, sort of an image of what's going on. This is continuous for all values of x, y. You know the upside down for all, right? Dr. Nichols showed you that, yes, at some point? Everybody's good with that? Okay, continuous for all values of x, y, where x, y, the point, is what? What can you use to, how would you describe my picture? Where does my point x, y have to live? Yeah, inside a circle or on. I mean, it's actually less than or equal to inside or on. So if you want to put /on, inside on a circle of radius 3. I need one more detail. Centered at the origin. What was that? Okay. And of course, you could say centered at 0, 0 if you don't want to say centered at the origin. But this is the description. I mean, this is exactly where the function's continuous, right? It's continuous in this particular sort of spatial image. All right, everybody good? Okay. Now, if you end up with an equation and you had a less than or equal to sign, you might say something like it's above the line y equals x, right? Something like that. You might even have something where you can't have it equal to the 9. Like if this had been the same thing but it had been in the denominator, we actually couldn't have the square root be a 0, right? Because we get 0 on the bottom. So strictly it would have to say inside the circle. It couldn't actually be on the circle. So those kinds of details. So when you're working on the continuity, go ahead and write some sort of a description down of what your image actually is looking like, okay? All right, homework set. All right, this is on page 831. Numbers 6, 7, 9, 12, 15, 20, 25, 28, 31, 36, 37, and 40. Dozen. It just looks like a long list. All right, so everybody have this written down?